In this video, we're going to begin discussing measures of position. We've already discussed measures of central tendency, which were mean, median, mode. We've also already discussed measures of spread, our variance, our standard deviation, and everything, along with range. So now we're going to begin our study of measures of position. Measures of position mean where does one data value lie in relationship to all the other data values in the set. The first one that we're going to look at is what we call a z-score. A z-score, or a normal score, represents the distance that a data value is from the mean in terms of the number of standard deviations. So a z-score of 1 means that the data value is 1 standard deviation away from the mean. When you're looking at this, z-scores can be positive and can be negative. Okay? We obtain it the exact same way for population versus the sample whenever we're given a variance. So when we're looking at the z-score for population, we have our value minus the population mean divided by the population standard deviation. When we have a sample, it's still going to be a lowercase z, and it's going to be x, which is our data value, minus x bar, which is our sample mean, divided by s, our sample standard deviation. The z-score is unitless, and it's because whenever we divide minutes by minutes or inches by inches, they cancel each other out. They divide out. And so z-score is unitless. It has a mean of 0 and a standard deviation of 1. Again, a z-score of 1 means that it is 1 standard deviation from the mean. When we're looking at z-scores, the middle is 0, which is our mean. 1 is the mean plus 1 standard deviation. A positive 2 is the mean plus 2 standard deviations, whereas a negative 1 is the mean minus 1 standard deviation. A negative 2 represents the mean minus 2 standard deviations. So this right here are our z-score values. Here, as we already discussed in examples with the empirical rule, we've just added and subtracted a standard deviation. When we're talking about z-scores, we always round z-scores to 2 decimal places. So always round the z-score to 2 decimal places. This is actually more beneficial later on, but part of the reason is because of some of the tables and charts that we use are already rounded to 2 decimal places. So we just want to keep that consistency throughout. And so we're always going to round z-scores to 2 decimal places. Let's look at an example. The mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. Data based on information obtained from the National Health and Examination Survey. So we know this from this particular survey. Who is relatively taller? Because we're asking for relativity, that means compared to the mean height. We want to take into consideration the standard deviation as well, because remember, the larger the standard deviation, the more spread out the data values are. So we're going to first look at Kevin. And Kevin is 83 inches. So his z-score is going to be 83, because that is his height, minus the mean of males, which is 69.1, divided by the standard deviation of males of 2.8. Please make sure that you follow order of operations. So we're going to take 63 minus 69.1 first, and we get 13.9 divided by 2.8. So the z-score for Kevin, when rounding properly, is 4.96. Recall that this is unitless. Now we're going to look at Candace. Candace has a height of 76 inches, minus the mean for females of 63.7 divided by 2.7. So 76 minus 63.7 is going to give me 12.3 when I do that subtraction, divided by 2.7. So her z-score is a 4.56. Now, in order to determine who is taller relatively, we just look at their z-scores, and the larger of the z-scores is taller relatively. So Kevin is relatively taller. Now, recall from previous studies the empirical rule. When a population has a histogram that is approximately bell-shaped, then approximately 68% of the data will have z-scores between -1 and +1. That -1 is subtracting 1 standard deviation. The +1 is adding 1 standard deviation. So approximately 95% of the data will have z-scores between a -2 and a +2, which leaves us with approximately 99.7% of the data will have z-scores between -3 and +3. This leaves us the 0.15% having values larger or smaller than -3, +3. Practice calculating some of the z-scores, and let me know if you have any questions.